Let's have some revolutions. Well, the revolutions we're going to talk about today and in the next couple of classes have nothing to do with people getting out in the streets and complaining and killing each other, thank goodness, but with something much more peaceful and interesting. And that is the idea of revolving something around something else. Okay? What we're going to be looking in this class is the idea of what do we get when we rotate something around something else, and how do we measure that something else. Too vague for you? I agree. So let's look at a little bit of a more formal and more clear definition of what we're talking about. First of all, let me say what a surface of revolution is. In order to get a surface of revolution, what we need is we need to start from a curve. So we're going to get some kind of a curve, and we're going to rotate that curve around some straight line, which we call an axis. Or axis of rotation. In this particular example, you'll notice that the curve actually touches the axis. We'll see later on, particularly in the examples that we're going to do in class, that this need not be the case. However, just for simplicity and just to give an idea visually of what's going on, let's assume that this is the case here. So let's take this curve and let's rotate it around this axis. Okay. Now I realize this is a very crude kind of animation. It's the best I could find on my program. But if you go online and you just Google surfaces of revolution or surface of rotation, I'm sure you're going to get some much better videos or graphs to give you an idea of what we're talking about. However, even in this simple example, I'm sure that you'll be able to visualize in your head that if you're taking that curve and you're rotating all around that axis, we're going to end up with something that will look like a bowling pin. And the question we're asking is, what is the surface area of this bowling pin? Okay, so for instance, if we want to paint this bowling pin, how much paint are we going to need? Now that may look like a silly question to ask, because if we need to paint some bowling pins, all we're going to do is buy some paint, and then if it's too little, we buy some more. If it's too much, we're going to have some left over. I realize that, but the point is still, how can we compute that surface area? Similarly, let's say we take this particular curve and we rotate it around this axis. What are we going to get? Can you visualize it in your head? Yes, it's a wine glass. And similarly still, if we get this curve, okay, and this time we're going to rotate it around a horizontal axis, what are we going to get? Well, I'm sure it won't take you long to figure out that what we're going to get is some kind of a bottle. And actually, we're also going to get a miracle, a bottle of white wine that pours into a glass red wine. Well, either a miracle is a little trick or just lack of better graphics. All right, so let's see a little bit more seriously, how do we compute the surface of any one of these objects? Now, in order to figure out how to compute this area, we're going to have to understand what is the building block of the whole procedure. Okay, the building block actually turns out to be a cone. Okay, in particular, not even just a cone, but something else that we're going to call a frustum of a cone. Okay, so how do we get a frustum of a cone? First of all, what we're going to do is within this big cone, we're going to imagine a smaller cone. Okay, so a cone which ends a little bit earlier, not quite at the bottom base, but at some base which is a little bit higher up. Then what we're going to do is we're going to erase, delete, get away all the top smaller cone. What we're left with is what we call the frustum of a cone. And you may have seen an object like this in a circus where they usually have elephants or other such animals stand on top of one of those things. Okay? So what we're talking about is actually the surface of this thing. So that would be the lateral area of this frustum of a cone. Well, it turns out from basic geometry, and this is a little exercise that I would definitely encourage you to do on your own, okay, is to show that if this frustum of a cone is done in such a way that the bottom base is a circle with radius big R and the top base is a circle with radius little r, and the side of that frustum, that slant little piece, has length L, then the surface area of that frustum is going to be given by pi times the sum of those two radii times L. Again, as I said, it's a little exercise proving this formula, which involves just using the formula for the surface area of a cone and subtracting one from the other and doing a little bit of algebra. It's not very difficult, but it is a good exercise for you because it involves a whole bunch of skills and formulae from your past. Now, we're going to do some further algebra on this one. What I'm going to do is I'm going to do something quite simple, a very old trick, that is multiply and divide by 2. Now, why would I want to do that? Because now look at what we have in that fraction in the middle. That's little r plus big R over 2. Well, that's just the average of those two radii. And because my side, that little segment L, is a straight line segment, we're talking about a cone, what we're talking about here as the average of those two radii is just the radius of the circle which is right in the middle. So we're going to call that R upper bar for average radius. So the area of this first term is going to be 2 pi times this average radius times the length of the segment L. All right, so this is what we're going to be using in order to construct the area of the whole surface. Because if you look at the curve that we were rotating in order to get that bowling pin, so let's just focus on the curve, and we take a very little piece of that curve. Actually, it's a bit bigger than what I have in mind, but just so that you can see it. Now imagine taking that little straight segment and rotating around the axis of rotation. What do we get? Well, we get exactly the first term of a cone. And that means that in order to figure out the surface area of the whole the area of the whole surface that we're generating by rotating that curve, what we're going to be looking at is a whole bunch of those frusta.